the agenda that I'm going to use for today, you see deck level observations. I'll talk about the wind, the wave, the current, the sky, because that's where all the weather takes place. Fog, weather data, data sources that you have available to you. Storm tracks, and I'll just use the example of the U.S. East Coast for that. And then a few notes on further study that you can take with this. So let's talk first about deck level observations, and just picture yourself standing on the deck of your boat. You're underway, and what are the things that you can actually see, and what are some of the meanings of these things? So first off, we have wind, the direction and the strength of the wind, and that's a primary item of interest. But the more important issue really is the wave direction, height, and period, or the speed of the waves. There are the currents that you have to deal with, the water currents, the color of the sky and the progress of the colors in the sky and the clouds, and how these sky images are moving and what do they mean to you. Lightning that you see in the distance and the approach of lightning. And I know that so many times at sea we see lightning and you say to yourself, well, that's a long way off, but surprisingly it's going to be on top of you before you know it. Squalls, which are generated by local weather systems. Visibility, fog, mist, rain. Air temperature and dew point, which produces fog. Seawater color, currents and temperature. The barometer, what's the barometer doing? Rising, falling, steady. Radar observations. And the condition of the sea surface, that is there sargasso weed, leaves, branches, logs? These are all considerations that you take into account when you're sailing, and some of the things that you observe from the deck level. So let's take these one at a time and talk about them in a bit more detail. You're interested in changes that occur to each of these things. In other words, these are not static. The weather is never static. Like someone said years ago, if you don't like the weather, just wait a few minutes and it will change. So you want to be aware of changes to weather conditions and to correlate these changes with each other of these various factors. So let's talk about wind. As I'm sure most of you know, it's caused by pressure gradients, and you have low pressure systems, high pressure systems, you have ridges and troughs, you have temperature and density differences of the air itself. These things cause wind when wind flows basically from high pressure to low pressure. And the wind, of course, produces sea surface waves. These waves are the locally generated waves where the wind is taking place, but also the wind will generate swells that travel a long distance. If you have storm force winds that you're dealing with, you'll end up with very steep, confused seas locally where the storm is, and then the swells will flow out from that point and really flow entirely across the ocean and affect other areas of the world. So let's look at this first off for the Beaufort wind scale, which is commonly used. And the Beaufort wind scale has actually had quite a history. That initially it was based on the condition of the sails on the ships. With the wind of a certain strength, a Beaufort 3 wind strength, they could have certain sails up, and a Beaufort 7 strength, they could have fewer sails up. With time, this has evolved into really sea state more than anything. But we also correlate wind strength, the wind velocity, with the Beaufort numbers. So you see that Beaufort 3 signifies winds in the neighborhood of 7 to 10 knots. And Beaufort 12, beginning of hurricane force winds over 64 knots. So Beaufort 5 is a nice, comfortable sailing breeze, a fresh breeze. You really go charging along very nicely in 17 to 21 knot winds. But these are the wind scales just for reference, and we'll be referring to Beaufort wind scales later on. So you might keep these numbers in mind. Wind direction, high pressure towards low pressure. So that's the direction of flow generally. But also there's the inward circular motion towards the center of a low pressure system, and the outward circular motion away from the center of a high pressure system. And I'll show some diagrams that show this. And there's also the Coriolis effect, which very significantly affects the wind direction and causes really the circular patterns that produce low pressure systems. Let's talk about Coriolis effect for just a moment. It causes the rotation of the air around the center of a low. And you see, as noted here, counterclockwise in the northern hemisphere, clockwise in the southern hemisphere. Now, in the northern hemisphere, any flow to the north or south will bend to the right of its path relative to the Earth. I'll show you a diagram of this in a second. And the effect of this will increase towards the poles as you get towards the poles. And as you see here in the southern hemisphere, it bends to the left of the path. So here's a diagram of Coriolis effect and how it actually works. And this really gets down to your frame of reference that you're observing the wind from. Now, if you look at this diagram of the Earth, here's North Pole, South Pole, here's the equator across the middle. The equator is moving to the right. And since the Earth is roughly 25,000 miles in circumference at the equator, and since it rotates 1 revolution per day, it's going to rotate at roughly 1,000 miles an hour at the equator. Now, the air is traveling with the Earth's rotation, and thank goodness for that, because otherwise we would have a 1,000-mile wind blowing in our face standing at the equator. But the wind, the atmosphere basically is rotating with the Earth in that direction. So a little parcel of air, and I have a little block here showing a parcel of air at the equator, block A, and it's rotating from left to right along with the equator. Okay, but that's a parcel of air. Now, if that parcel of air A decides to move north for some reason towards the pole, it's actually going to be traveling to the east faster than the Earth below it. Now let that sink in for a minute. This air is going to travel north to point B, but when it's at the equator, it's traveling at 1,000 miles to the east, 1,000 miles an hour to the east. But as we get further to the north, it's still traveling at 1,000 miles to the east, but the Earth may be traveling at only 600 miles to the east at that point because there's a smaller circumference. So this parcel of air will actually get ahead of the Earth's rotation in the easterly direction. So therefore, as it flows from the equator towards the pole, it will turn to the right of that northerly path. Okay? In the southern hemisphere, the same thing will happen. It will turn to the left of its path in this direction. So this flow to the right of its path is actually what causes the circulation of some of the low pressure systems. And by the way, we'll see in a little while, it also affects the rotation of the currents at sea. So let's look at a low pressure system. And a low pressure system has warm air rising due to lower density than the cool air surrounding it. Okay, so we have an area where we have warm air for some reason, and that air, since it's warm, it's a lower density, and it therefore rises. Well, when that air rises in the center of this low pressure system, other air has to flow in to fill the void from the surrounding air. When this air flows in, it bends to the right of its path, as the Coriolis effect showed us. So when it bends to the right, it actually produces a circulation within the center of this low, and this entire system begins to rotate due to the Coriolis effect. And as mentioned here, it's in a low pressure system. It's counterclockwise in northern hemisphere, clockwise in southern. And in a low pressure system, the wind speed increases the closer you get to the center. So when you're way out here, you have the circulation, but it's a slower speed than as you get towards the middle. It accelerates towards the middle. A high pressure system does the opposite. In the northern hemisphere, you have cooler air than the surrounding air. So that cooler air is more dense. It sinks and therefore flows out of that region. As it flows out, it also bends to the right of its path and therefore circulates in a clockwise direction, northern hemisphere. Okay, so that's low pressure and high pressure systems and how they develop their spin. Now here's more of the structure of a low pressure system, northern hemisphere. And low pressure systems are generally formed by the collision of a warm air mass and a cold air mass. And where these two come together, it produces, eventually it develops into a circular pattern. And this circular pattern is shown here, and the construction of a low pressure system. Basically, this line here with the triangular barbs on it is a cold front. We'll talk more about cold fronts in a little while. And here with the round barbs on it is a warm air system. So here you have cold air and warm air. Where they come together, we begin to develop a circular pattern. And these circles that are shown here are isobars, that is, lines of equal barometric pressure. So 12 indicates 1,012 millibars. So 1,000 being 1,000 millibars. So they don't print the 1012, they just print the 12. So 12 signifies a barometric pressure of 1012, 10.8, 10.4, and then if it goes below 1,000, you'll see 9.6, 9.4, 9.2, and so forth. And so these are the pressures. And here, these straight lines are continuation of these isobars, but they become straightened out in this region. And so this first straight line is 10.04, 10.08, 10.12. And the direction of these isobars indicates basically the direction that this entire system is moving. So here's an arrow here that's parallel to these isobars, and that's the direction that this entire system is moving. Okay? Now let's look at the wind. The blue arrows indicate the wind direction. The wind will bend, it won't go exactly parallel to the isobars, it'll actually bend in towards the middle a little bit, as the arrows show here. So as you come around this, this low pressure system, the wind direction is changing, always circulating around and always pointing somewhat in towards the center. The air in these areas, first off, let's look here. Cool air, cloudy, steady rain. Warm air, partly cloudy. Now here's cooler air, heavy clouds, driving rain up here, but here's where it's starting to clear, and here's in back of the cold front. And you have cold air, brisk winds, clearing skies. And you notice a significant change in wind direction from this zone to this zone. And this is something that's very significant to sailors when a low pressure system comes barreling through. This change in wind direction when the cold front passes. So that's the basic structure of a low pressure system. Of all the things in weather, the thing that you should best understand is a low pressure system, the structure, the movement, and the functions, if you will, of a low pressure system. It's vitally important to a sailor offshore, to a sailor anywhere. Let's look at another aspect of this low pressure system, and that is the dangerous semicircle. Now, you notice with the red arrow here that the path of this low pressure system is as shown. And to the right of the path, to the right of the low center, is what's called the dangerous semicircle. It's stronger winds for a couple of reasons. One, the isobars are closer together, and therefore the wind pressure gradient is greater. Therefore the wind strength is stronger. But secondly, the velocity of movement of the low pressure system itself, the speed that the system is moving, adds to the wind speed. So the speed of this red arrow is going to add to the speed of this blue arrow, and you're going to have stronger winds here for that reason as well. And here on this left side of the low pressure system, this wind will subtract from the speed of movement. So you'll have a canceling somewhat of the wind on the left side. So the right side is usually the more hazardous part of a low pressure system. Now, in the Bullseye, as a low approaches you may be directly on its track if the wind direction remains fairly constant and the barometer continues to fall. Okay, so let's look at that in this diagram. Here's your boat. Here's your little red boat here, and here's a low pressure system approaching and moving in the direction of this arrow. And as you see by this blue arrow, that the wind that you're experiencing is roughly from the east. It's on your port bow in this picture. Okay. Now, the low pressure system has now traveled over you, and the wind is still basically going to be from the east. It may be starting to shift to the northeast somewhat. And as we go one further step, as the wind passes you, it shifts to the west, to the northwest on your starboard side. So let's look at this again. The wind has gone, as the low crossed over you, the wind has gone from your port bow to northeast and maybe north to northwest. Okay? So the wind has, we call this backing. The wind has backed. If you stand on the deck of your boat and you face forward, the wind in this picture is on your left side, your port side, the port side of the boat. In this picture, it's coming from astern. In this picture, it's coming from your right side. So the wind has backed around the circle, and you're now experiencing these strong northwesterlies that come with the movement of the cold front itself. So that's in the Bullseye. And what happened here is that I didn't draw all of the isobars in this picture, but what has happened here is when the low pressure is here, the low pressure system is here, your barometric pressure is a certain level. Let's say it's 1004. And as the system gets here, you may be 1,000. So the pressure has reduced on this path from here to here, but the wind direction has remained fairly constant. Okay. Now let's go on to, if the low is passing north of you, again, northern hemisphere, the wind will veer, that is, move clockwise. So let's look at this example. Here, again, is your boat. Here's a low pressure system, and it's passing north of you. It's moving in the direction of the red arrow. And here the wind is blowing southeast on your port bow. Okay? As it travels further, it has shifted. It has veered to your starboard bow. And further, it has veered to your starboard quarter. So what has happened is the wind has from southeast to southwest to northwest. Okay, the wind is the low is passing north of you. But also in that scenario, the barometric pressure has changed, because as you go from here, let's say you're at 1004 and the low is close to you, you now might be 1,000, and here you're back up to 1004 again. Okay, you see that pressure difference as well as wind difference. So that's a low passing north of you. Now let's go a low passing to your south. The wind will back or move counterclockwise. So here again, here is a low south of you, and the wind is blowing from the east or northeast. The low has moved to this point, and the wind has backed to north, okay? And the wind has backed further to northwest. The low has passed south of you. And here again, the pressure is going from 1004, a little lower here, and higher again here. So you see it. So the two factors, the change in wind in barometric pressure, as well as wind direction, helps to tell you where that low is and what you should be expecting. And this all relates to Buys-Ballott's law. B-U-Y-S. Ballott's was actually the name of a person who discovered and codified the idea of change in wind direction and the location of the low. And basically, let me go back a few slides here. Oops. If you face the wind, the low is going to be roughly to your right side. Now picture yourself here facing the wind, and the wind is going to be roughly to your right side. So here then is an extreme low pressure system, which we all recognize as a hurricane offshore, coming across the Caribbean here and heading on towards Florida and the Georgia coast. And it's huge. And you can see the circular pattern, and the circular pattern, as we mentioned before, is produced by the Coriolis Effect. I'll show you more about the hurricane here in a few minutes. The hurricanes are very intense and destructive low pressure systems. Now they usually develop in the North Atlantic along the Intertropical Convergence Zone, ITCZ. As the zone moves north during late summer. Now they also sometimes develop outside of the tropics. And if you go, you all have the printed handout, so if you go to this website, you'll find a guide that gives a lot of good information on hurricanes and dealing with hurricanes. But let's look at the Intertropical Convergence Zone first, ITCZ. It's basically the zone between the northern and the southern hemisphere. We have the equator here, and as this diagram shows, the ITCZ lies along the equator. But here's a picture of how that ITCZ moves with the seasons of the year. This dotted line is where it is in January, and the solid line is where it is in the summer. And you notice on the west coast of Africa that it has moved quite a bit north from the equator. And you recall in discussing Coriolis Effect that we said that the Coriolis Effect increases as you go towards the poles from the equator. So what happens is that the ITCZ is an area of a great instability, weather instability. That is, you have a lot of warm air, warm moist air, it's rising, and therefore we have the inflow and we have the Coriolis effect. And the fact that this zone has moved further north in summer means that the Coriolis effect will be greater, and therefore there's a greater probability of developing an intense low. And this is why, as we go from July, August, September, we get the peak of hurricane season. It's because of the movement of the ITCZ. And you can discover more of it by looking at this website. This is a summary of North Atlantic storm data that I extracted from the pilot charts, and I'll show you pilot charts in a little bit. But basically, this is a statistical summary, historical summary of tropical cyclones, hurricanes, and gales. And if you're going to sail, let's say, from Norfolk to Bermuda, you say to yourself, well, when's the best time to go? Well, let's look at this. In the month of April, May, June, and so forth, the number of tropical cyclones, now remember, this is on average. So this says in April you have practically none. But as the season progresses into the summer, you see the number of tropical cyclones increasing, reaching a peak of 5 in September. Now this resulted from the ITCZ moving north. A certain number of these trop cyclones will intensify to hurricanes, and you see the height of hurricane season, September. And there are gales. These are gales reported from ships, and gales meaning 34 knots or greater. Percent of reports that are reporting gales, and most of these are coming from northern weather systems as opposed to tropical weather systems, and you see these reducing as we get towards summer. So if we're going to choose the best time to sail to Bermuda, well, not surprisingly, June is the month that most people choose, and it has some possibility of hurricanes and tropical cyclones. It has some possibility of northern system gales, but it's kind of the optimum balance between the both of those. And this information, as I say, is extracted from the pilot charts for the Atlantic Ocean. Here's an image of the various, this is for the year 2009, and it shows the tracks of the various hurricanes that took place that year. Here's Bermuda here, here's Cape Hatteras, here's Norfolk, and you see the track of the various hurricanes that are shown here. And most of them are developing here off the west coast of Africa, near the Canaries, and traveling west, and then doing something here. Some of them go inland, some of them bend and go over to England. Okay. Now, hurricane track avoidance, again, northern hemisphere. And here's a picture of a hurricane, a low pressure system. It's a hurricane, and it's traveling this way. And you remember the right-hand side of that is the dangerous semicircle, the right-hand side of the track. But in order to avoid the worst of that hurricane, the recommended maneuvering actions for a boat is, if you are on the right side of the track, put the wind on your starboard bow. You see this? If you keep the wind on your starboard bow, you'll be sailing in this direction as the low approaches. If you are on the left side of the track, and with the rules I showed you before about wind direction changes and barometric changes, you can judge whether you're right or left of track. So if you're left of track, you want to put it on your starboard quarter, northern hemisphere. Okay, and it's the opposite for southern hemisphere. And if you look at this website, this is the NGA website, and you can actually download Beaufort in its entirety, Beaufort, which is like the Bible for sailing, navigation, weather, and so forth. And from chapter 36, you'll see a lot of discussion on hurricanes. You can also download from this website, Mariner's Guide PDF, this guide. It's a multi-page guide that gives you a lot of information on hurricane awareness and how to deal with hurricanes, how to recognize some of the pitfalls and how to deal with them. Shown here, two basic options. One, if you have access to internet images, the cone of avoidance is actually shown on the predicted track image that NOAA publishes. So in this case, here's the storm here in northern Florida, and you can see the forecast track and this cone that they've drawn around this track, and that's the cone that you want to avoid. You want to maneuver your boat to stay out of that cone. If you don't have internet images and you have only the voice forecast over single sideband radio or the NAVTEX, the predicted track is given in a narrative, and you need to apply the Mariner's 1, 2, 3 rule to determine the cone of avoidance. Now let me show you all of that. Here's a forecast of a wind track that's come over voice radio or the NAVTEX. And it says, tropical storm, winds of 34 knots, gale, extend out to 120 nautical miles from the center. Then it says, our initial prediction is that on the 8th, that is the date of 8, let's say that June 8th, at 0600, the storm center will be located at 30.0 north, 68.2 west, and the maximum winds are 40 knots. 12 hours later, at 1800, it's going to be at this location, 45 knots max. 24 hours from the initial forecast, at 0600 on the 9th, it will be here. 48 hours, 2 days after the initial, it's forecast to be here. 72 hours, 3 days, it's forecast to be here. Now recognize that these are forecasts. These are not actualities. So at that time when they gave this report, this is what they expected. But this may change as time progresses and they gather more information. But you take this information, and in order to apply the Mariner's 1, 2, 3 rule, which will develop a cone of avoidance for you to avoid, the first thing you do is plot the positions. So here I've plotted the initial position, 12 hours, 24 hours, 48, 72 hours. So this is where the storm is predicted to be in those time periods. Now you recall that from this it said the gale force conditions extend out 120 miles from the center. So we'll take 120 miles and draw circles of 120-mile radius around these points. And I've drawn those in here. So these are the gale force wind circles with a radius of 120 miles. The next step is to apply the Mariner's 1, 2, 3 rule, which basically is 1 day out, that is at 24 hours, you add 100 miles to the radius. 2 days out, you add 200 miles. 3 days out, you add 300 miles. And basically, that is to deal with the unpredictability of the hurricane track. So here's what you would do 1 day out. You would apply this radius, so it would be 120 miles plus 220-mile radius at 24 hours from now. And 2 days from now, 48 hours, you would apply 120 plus 200, 320. And 3 days from now, you would apply that circle. 120 plus 300 is 420. So these blue circles establish the cone of avoidance that you would like to avoid if at all possible. And in order to stay away from the possible track changes of the storm, because what they predict here on this date may not be the case when they get later information from now. But this is felt to be a conservative estimate of where the storm might be, and it's used in planning your route of avoidance. Now let's talk a little bit about local winds. We're still on winds. There are thermal winds, and these again are due to temperature density differences and also the topography. of the land. As we talked about before, warm air rises, cool air sinks. We have sea breezes, land breezes, valley breezes, mountain breezes, downslope breezes. But all of these relate to changes in density. You also have geographic wind effects. The wind can twist to follow the long axis of a river. It may be blowing partly across the river, but as it comes to the river, it's going to basically flow more towards the center line of the river. Not necessarily on the center line, but in that direction. Wind refraction flowing offshore bends toward the perpendicular to the shoreline. And wind will accelerate in narrow valleys. Okay, let's look at cumulus clouds. Cumulus clouds indicate rising air, and thus they indicate a small low pressure area. Now the cloud does not cause the low pressure area. The low pressure area causes the cloud. Okay, basically we're taking warm moist air and it's rising to a higher altitude, cooling off and causing a puffy cloud. But these clouds indicate local changes in wind direction. And basically, wind in this area will be back, shifted counterclockwise. If you're sailing close haul towards the cloud, you'll be lifted on port tack and headed on starboard tack. Okay? You got to draw yourself some pictures to get your mind around that. Let's talk about waterspouts. Now there's two types of waterspouts that we basically see at sea. One is from tornadoes, which are exactly the same as tornadoes on land. They develop from up above, from the clouds above, and they touch down. And the people down in the southeastern United States have just experienced terrible tornadoes, as we know. And these can be also destructive at sea. And we also have fair weather waterspout develop from the surface level and develop up. And here are tornadic waterspouts. These are very, very destructive. They develop from the cloud layer and they touch down. You can have wind speeds of well over 100 miles an hour. I think in these recent tornadoes in the south, I thought I heard that they said up to 150 knot winds. So these can be very destructive. Here's a fair weather waterspout, and it develops from the surface up, and it can also be destructive. So don't minimize the potential danger of fair weather waterspouts. And what I'd like to shift to now are waves, because the thing that really gives us significant concern at sea are the waves produced by the wind. And we have two terminologies here, two terms that we use. One are seas, commonly referred to as waves, but the seas are local. They're wind-driven from nearby winds. And they're prime interest to mariners, and what happens is that they're very confused. They're very steep because waves are being generated by the local winds, and they bunch up on one another and become steep and hard to handle. Swells, on the other hand, are long distance. They're storm driven from a distance away, and you can use a swell to imply or infer the location of a distant storm, and the height diminishes the further they travel. Also, the speed changes. Tsunamis are caused by geologic disturbances, and we've seen a lot of those. Here's another website that talks a lot about waves. Here's a picture from Wikipedia on locally generated waves. You can see a very confused sea. You can see steep waves interfering with one another. The ship is having a significant time maneuvering these waves. Let's look at local storms. They cause confused and violent wave action, steep, closely packed. Waves travel out of the area, as I mentioned, and you can have a storm here on the west coast of Canada. near Alaska, let's say, and here you have waves traveling all the way out to Hawaii and beyond. And I'll show you some other pictures of this in a minute. Now let's look at wave terminology. First off, the length of a wave, as you see from the picture, is the distance between crests in feet. Here's the still water level, and the height of the wave is from the peak to the trough. Okay? And the period, that is the time in seconds for successive wave crests to pass a stationary object. So the period is the time for 2 wave crests to pass. The steepness of a wave is the ratio of height to length. And here's wave steepness. And here's the height. And here's half the length. And that gives you the steepness of a wave. We're going to be using that terminology in a few minutes. Now, wave steepness will increase when the wind blows against the current. Okay? Wind blowing with the current will decrease the wave steepness. This is the actual steepness of the wave. This next bullet refers to the effective steepness. Let's say there is no wind at the moment, but you have waves. The effective wave steepness will increase depending on the direction that the vessel is traveling. So a vessel traveling in the direction of the waves, the effective steepness will reduce. If the boat is going in the opposite direction, it will increase. When a boat is going in the direction of the waves, it will decrease. And here again is a website related to this. Wave circulation, now the thing you have to keep in mind is that the water does not flow horizontally with the wave. The wave is actually a pile of energy that's traveling across the surface of the water. And let's look at this diagram for a minute. Here are waves traveling from left to right, and here's a ball floating in the water. Now, here's a wave crest here to the left of the ball. As this wave crest moves to the right, it picks the ball up, but the ball does not flow to the right. The ball basically stays in the same location. It moves a little bit to the right and left, but not much. And when the wave passes, the ball is back down here. So the water basically rises and falls with the passage of the wave, but it does not move significantly in the horizontal direction. Okay? Let's look again at this diagram. So the surface water, since it's standing still and the wave is moving, the surface water actually flows up the incline as the wave moves from left to right. With respect to the wave, the water is going up. Okay? And on the back side of the wave, the water is coming down. And there's actually an acceleration here of this water because it's covering a greater distance in a given period of time. So it accelerates up the hill, it decelerates down the hill. Okay? And let's look at wave trains. We have different waves generated by different sources, and they may be at different periods, that is different wavelengths and different speeds. But as 2 different wave trains combine, they'll produce a net effect as shown in this example. So the dotted wave and the solid wave are traveling at different speeds, and you see that their frequencies are different, and therefore one wave catches up to the other. The dotted wave is going faster than the solid wave. Well, back here, the waves reinforce each other, so the combined effect is higher. But here, they cancel each other, so the combined effect is lower. And this is why you will see at any given time a significant difference in the waves that you're experiencing. And I'll show you more on that in a few minutes. Wave speed. Measure the time between successive crests. As I mentioned before, is period in seconds is between successive crests. Short periods, locally generated waves, for example, 1 second. Long periods indicate wave swells generated by a distant storm. Might be 16 seconds between crests. Wave speed in knots is 3 times the wave speed in period. So if you have a 10-second wave, it's traveling at about 30 knots. Here's a download from the NOAA website on weather, and this is showing wave period, that is the speed of the waves, and the colors indicate different speeds. If you look on the right here, you see the color code, and down at the bottom you see the blue, the dark blue is a 1-second wave, and up top the pink is a 21-second wave. So over here in the dark blue off the coast of Delaware is a storm generating waves, and here there are 1-second waves. But as we come across the Atlantic Ocean, the wave period gets longer, so that here as we approach Spain, we have, looks like 13-second waves, okay? So we've had this outflow of storm swells going all out from this this storm that's generating these waves and becoming swells as it flows fully across the ocean to all parts of the ocean, okay? Now keep in mind that this wave, this tan-colored wave, 14 seconds, approaching the coast of Spain, is traveling at, well, 13 or 14. 3 times 13 is 39 knots as it crashes on the shore of Portugal here. Okay, wavelength and speed. The length in feet is 5 times the period squared. A 10-second wave is 500 feet long, regardless of its height. So length equals 5p squared, 5 times 10 squared, 10-second wave, 5 times 10 squared equals 500 feet long. Speed in knots, as we said before, 3 times a period is, for that wave, 3 times 10 is 30 knots, okay? Swells that are traveling across the ocean, like I showed you in that previous diagram, they'll reduce in height about 50% a day, and they'll increase in period about 2 seconds per day. Wave energy is proportional to the wave height squared. So energy of the wave is a constant times the height squared. So a 15-foot wave is 5 times the height of a 3-foot wave. Therefore, 5 squared becomes 25 times the energy of a 3-foot wave. A 15-foot wave is 25 times the energy of a 3-foot wave. Okay? Here's a reference for that as well. Now, wave height drivers, as we talked about before, in open ocean we have wind speed, wind fetch, wind duration, and currents. Near land there's also shallow waters, narrows, tides that affect wave height. Breaking waves. Taller, steeper waves will break sooner. Long swells, like tsunamis, generally don't break until tripping on shallows. They're not a problem to boats at sea, but they're a big problem to boats near the shore and inland. But it's not just a matter of height, because other factors include, as we talked about before, the current in opposition to the wind, the suddenness of wind increase, how suddenly has this occurred, and air temperature. Colder air attacks the surface at a greater angle, thus imparting more energy to the water. Okay. Now ground swells begin to feel the bottom when the water depth is about half of the swell length. So a 500-foot wave will begin to feel the bottom at about 250-foot depth. The swell becomes taller and slower as it drags the bottom, and it will break when the water depth is equal to 1 to 2 times the wave height. So here's a breaking wave. This is a ground swell. It's being built up higher and steeper by shallower waters, and it breaks like this, similar to as occurs on the north coast of Oahu. Wave steepness and the wave movement is an issue for a boat pitchpoling. Here we have an image of a boat sailing down a wave front, but recall that the surface water relative to the wave is moving this direction. So as this boat plunges into the trough, it not only has to arrest its speed, but it's also resisting the water flow in this direction, which will depress the bow further. So sailing off in stormy conditions is not an advisable thing to do. Here's a ship encountering a 50-foot wave at sea. Now, NOAA wave height forecasts. The waves come in many sizes, as we saw, because we have trains mixing, we have swells traveling, we have locally generated waves, so you have a whole combination of wave heights at a given moment and a given location. NOAA reports wave height as significant wave height. Now don't be fooled by this term, because it's a very deceiving term, and I'll explain in detail why. It refers to the highest 1/3 of the waves at a given time and location, but it's not the highest waves. Significant wave height is the average of the highest 1/3 of the waves in a spectrum. Average of the highest 1/3. Now 1/10 of the waves will be 25% higher than the HS. 100 to the waves, that is 1 out of 100 waves, will be 65% higher than the average. Now let's just think about that. If you have a 6-second wave train, that means there are 10 waves per minute. That means that every 10 minutes you can expect a wave 65% higher than the significant wave height forecast. And the maximum height can be 100% higher. It can be double the significant wave height. So let's look at this. This is a Brett-Schneider distribution. It's a bell-shaped curve, and basically it plots the number of waves on the vertical scale and height of the waves on the horizontal scale. Okay? And this says that at any given moment, statistically, here's your most likely wave height here, because you have most waves of that height traveling. But here's the NOAA forecast height of significant wave height, HS. In other words, this height along this scale, here is HS, significant wave height. And this gray area here is 1/3 of all the waves in this distribution. And the significant wave height is the average of all of these wave heights. Okay? So here is HS as reported by NOAA. But here is the distribution of the remainder of this wave spectrum. Here's the height of 1/10 of the waves. So let's look a little further on this. Now, if you again go to Beaufort at this website, this chapter 33, you'll find this table, and this table will give you headaches, but there's a lot of information in it, and I'll just go over it briefly, and then I'll extract some information from it and show it to you. On the left-hand column is the fetch in miles. That is the distance of open water that the wind is blowing, 10 miles, 50 miles, on up to 1,000 miles, fetch. Across the top is the Beaufort number, 3, 4, 5. Here's 17 to 21 knots, the 5. Here's just below hurricane, the 11, okay? Then THP. T is the time, that is the period, I'm sorry, said that wrong. The duration of the wind blowing, that is 4.4 hours. Duration of the wind in hours. Here's the height, significant wave height in feet. Here is the period in seconds. And then eventually this wave can reach maturity at a fetch of 180 miles. Okay. Now I'm going to take this data and show you some curves that I extracted from it. Here's wind duration and significant wave height for a fetch of 10 miles. 10 miles of open water. And the left scale is feet, significant wave height. The right scale is hours, that is duration that the wind is blowing. And I can interpret this curve by saying, okay, a Beaufort 5 wind blowing for about 3.5 hours, a little over 3 hours, will produce a mature significant wave height of about 3.5 feet. So a fetch of 10 miles, Beaufort 5, blowing for a little over 3 hours, produces mature waves of about 3.5 feet. Significant wave height, okay? Same thing, a fetch of 500 miles, feet, height, duration, hours on the right. Beaufort 5, blowing for, it takes almost 60 hours at Beaufort 5 to produce a 9-foot wave. But Beaufort 11, blowing for 33 hours, will produce a 58-foot wave. So this is extracted from this table, okay? And as I say, that table will give you headaches. A few other things extracted from the table just to give you a perspective of it. Here is height for different wind strengths, height in feet. For different wind strength, the yellow is Beaufort 5, 7, 9, 11. And you see for different fetches how the wave heights will change. No matter what you do, a Beaufort 5 will level out at about 9 feet, regardless of the fetch. And these others will approximately level out. But you see the Beaufort 11 continues to build even with a 1,000-mile fetch. Here is wind speed, or I'm sorry, wave speed in knots versus fetch for different Beaufort numbers. All right, so the bottom is Beaufort 5. The speed will increase with fetch. as the fetch increases up to 25 knots. Okay, and likewise the others will build. The next thing I just want to mention are currents. Yeah, wind-driven currents, which we've been talking about. We have tidal currents, that is a swing in the tide elevation produced by the moon. We have gravity currents, that is flowing down a hill like a river. We have the Coriolis effect that we talked about before, and of course you have the tide tables and the current tables that have all the predictions for basically tides and tidal currents. But on a worldwide basis, let's look at this diagram. We show these great circulations within the oceans of the world. And let's look at the ocean, at the Atlantic Ocean, the Atlantic Basin, and we see these circulations. And you see these clockwise circulations in the ocean. It's the Coriolis that's producing the circulation. And part of this major ocean gyre are all these smaller currents that we refer to. Here is the Gulf Stream current, the Antilles current, Canary current, North Atlantic current. So these are all part of this major ocean gyre, but it is the temperature differences within the ocean, also salinity differences, and then also the Coriolis effect that produces this major ocean currents. And these are things that we have to deal with at sea. They can be quite significant. I'll talk a little bit more about currents in a few slides down the road here. But I want to go to the sky because this is where the weather takes place, and it gives us many signals as to what's happening. And you want to be cognizant of changes to these signals that it's giving. First off, let's talk air masses. And we have different designations of air masses. Continental polar, that means it's air that's flowing over land and is coming from a polar region, is going to be dry and cold and is given this designation, continental CP, continental polar. Continental tropical is going to be dry and warm for the tropical. Now maritime air flowing over the oceans is going to be moist, and again from the polar it'll be cold, maritime, tropical, moist, and warm. Okay, so those four basic categories of air masses. Air mass movement is what creates weather system, and the important point here is a moving cold air mass will push under a warm air mass, raising the warm air to colder altitudes and causing storms. A moving warm air mass will overlay a cold air mass, causing precipitation. And it's the collision of cold and warm air masses that produce lightning, thunder, squalls, low pressure systems, and so forth. Now let's look at a cold air mass movement into a warm air mass. And here on the left of this diagram is a advancing cold air mass. And it's pushing in under this warm air mass that's here, and it's raising the warm air mass to higher altitudes. And therefore the moisture in that warm air mass is cooled and produces cumulonimbus clouds and storm conditions that occur with that. We know commonly that we get severe prefrontal squalls that occur in advance of this condition, and we can have lightning, thunder, hard driving rain, and so forth. As you see here, this could be 50 to 300 miles ahead of the cold front, and this rain within the front of the cold front could be in the neighborhood of 50 miles or so. So that's the advance of a cold air mass. These are air mass symbols. We've already used these symbols, so this is no new news to you. But let's look at warm air mass movement. Here's a advancing warm air mass, and here's a cold air mass sitting here on the ground, and the warm air mass will ramp up over the cold air mass. The air mass will still hug the ground. And the advancing signs of this are the high altitude cirrus clouds, and I'll show you a picture of these. But as we come down the ramp towards the rain part, we go from cirrus to cirrostratus to altocume and so forth. And then the nimbostratus, which are the dark rain clouds. If you are out on a nice bright clear day, puffy clouds in the sky, and you see these real high altitude cirrus clouds, which are up here, well, these are the precursors of the movement of a warm air mass over your position, and usually within 12 to 24 hours you're going to have rain from seeing these. I'm talking in the temperate zone. So you'll go from cirrus to cirrostratus, altostratus, altocume, see the cumes are puffy, nimbostratus, the dark black rainy clouds, and then as that clears out you have stratus clouds, you have the rain tapering off. And here's a website for cloud classification. Cloud types, this is if you're entering in your log, you're writing the percentage of sky covered by the clouds and the type clouds that are up there. Here's are the different codes that you can use to make sense out of these, and other people will understand what you're writing. Okay. Now cloud heights, low clouds are up to 6,500 feet. You see mid-level clouds, high clouds go up to 43,000 feet. Now lightning thunder squalls, as we saw already, nimbostratus clouds and lightning that you see in the distance, these result from rising warm air to colder altitudes. Warm air mass rising to colder altitudes occurs by two methods. One is the cold air mass movement that we showed already, and the other is air mass heating on a clear hot day, as occurs in summer afternoons on Chesapeake Bay. And this is basically not because of an air mass movement, it's because of air mass heating on that hot, sultry day. And lightning thunder squalls can be very hazardous, can produce strong winds, and I have commonly seen these up to 50 knots, up to 60 knots. So your method for dealing with a lightning squall, these are things you have to think about and plan on how you're going to deal with a lightning squall. And basically what I do is I want to button up the boat from the standpoint of put my hatches in, I take down my head sail, or I furl my head sail, and I reef my mainsail to the deepest reef that I have. And I do not use the engine unless I'm near an obstruction that I have to avoid. But if I have enough open water, I want to sail through this and basically maintain the wind as a squall hits you, maintain the wind at roughly 45 degrees apparent wind to your bow, and simply follow the wind around as it moves past. And deal with that lightning squall, thunder squall in that manner. Thunderstorm development, developing stage as warm air is rising to higher altitudes. It gets to a high altitude, it has cooled off. This cool air now plunges down, and we have this cold downdraft. When you feel the cold downdraft coming at you, you know that you're very, very close to strong driving rain, because you're going to be hit by that storm at that point. But the cool air, the shift from warm air to cool air, is the key sign that it's imminent. Okay, let's talk about fog. Dew point is the temperature at which the air is fully saturated with moisture. And we use dry bulb temperature, wet bulb temperature as methods of determining dew point. And basically, the closer these two temperatures, the closer we are to a foggy condition. When the spread between dry and wet bulb, and I'll explain these in a minute, when the spread between dry and wet bulb is down 4 or 5 degrees or so spread, you are in fog territory, if you will, and it's imminent at that point. Fog is basically condensation of moisture in the air by either lowering the air temperature when you're in this 4 or 5 degree temperature spread. If the air temperature is lowered by some mechanism, or if the moisture in the air is raised, you'll have fog. And we would measure dry bulb, wet bulb by what's called a sling psychrometer, and this goes way back, and basically it's 2 thermometers, and you can take this, hold it by the handle, and twirl it to create a wind over the thermometers. And one thermometer has a cloth sock on the bulb. And just think of this, that if the weather is very dry and you put a wet cloth sock on this bulb, then a lot of moisture will evaporate from that sock and it will cool this bulb off. But if the weather is very humid, there will be very little evaporation. So when the weather is dry, you'll have a large spread because the wet bulb has evaporated a lot of moisture and therefore cooled the wet bulb. So you have a large spread. If it's humid, the evaporation is low, and therefore the temperature of wet and dry bulb are close. So when they're close, you're ready for fog. And here's a website related to that. This is a modern psychrometer, which I've never used. I've used these, but I've never used a modern one. Now, fog, there are several different terms used for fog, but basically it still gets back to this issue of when you're close to fog conditions, if you either lower the air temperature or increase the moisture content of the air, you'll get fog. Radiation fog and advection fog are very similar from the standpoint that the surface, that is the surface of the earth or the water, cools the moist air and the air condenses, cools the moisture in the air and the moisture condenses. Radiation fog occurs on clear, calm nights when the land is radiating its heat to the atmosphere, to the universe, really, and it cools off quicker than the air, and it cools the air below the dew point. So we've cooled the air in this case. This is similar, except we've had warm, moist air flows over a cold surface like cold water. And the same thing happens. We cool the moisture in the air and it condenses. Sea smoke is different in that wisps of water vapor coming off the surface of the water are condensed in the cold air. Haze, fine dust and salt particles suspended in air. Damp haze has water vapor in it. Mist, a fine drizzle. Smog, a mixture of smoke and fog. Okay, let's look at weather data. Now, there's lots of weather data that we have available on websites and all of that, but what do we have available on our boat when it's underway? Well, first of all, if you have the Ocean Pilot charts, which can be an education for you as far as what to expect. We have radar in which we can make observations of moving storms. We do have the internet before we go to sea, or if you have a really big boat, you might have internet on board, but for the most part, you can prep ahead of time. Near shore, you have VHF radio and cell phone weather reports. And now our cell phones, our smartphones have all kinds of apps to give you great weather information. Near coastal is a device called NAVTEX, and this is transmitted from shore stations, and it includes weather forecasts, frequencies, times of forecasts, and so forth, as well as the forecasts themselves for different areas. The NAVTEX is a very valuable device to have. You can get a Furuno NAVTEX for neighborhood of $400 or $500, and I feel for any coastal sailor it's an excellent thing to have. The NAVTEX reaches out about 200 miles to sea, but coastal it's great. And then offshore you have single sideband radio for voice forecasts, you have single sideband fax, and you have satellite, all kinds of satellite weather forecasts that are available at this point. You have DMA Pub 117, which is the radio navigation aids, and I urge that you download this or buy it in hard copy. Download it from the NGA website, and it has a description of all the different radio aids that are available and the content of those broadcasts. Ocean Pilot charts, as I said, that these are a historical record of past weather in all the oceans of the world. And here you go. You can go to this NGA website and you can download this Ocean Pilot chart in its entirety, or you can buy them in printed copy from U.S. chart agents. Now here's a typical page. If you squint your eyes and look in the upper left-hand corner, this is for November. Remember, this is a historical summary. So there's a page like this for each month of the year, for each ocean of the world, and also the Med and also the Caribbean, places like that. And it includes a historical summary of weather data. These big red lines on here are the boundaries of wave heights. These are wave height probability circles, and I'll show you some details on that. And these little circles here with the arrows are the wind roses for each location on this chart, for each 5-degree rectangle on the chart. They also have descriptions, and you can't read this very well, but I just want to point out that these descriptions describe, for example, wave heights that you should expect in this area. They describe gales that you should expect, extratropical cyclones that you can expect. Here are the wind rose explanations. What does this mean? And here's examples of it. Yeah. Here's a blow up a part of this chart, and this 30 refers to 30% of the time within that boundary there are waves of significant wave height of 12 foot and greater. Okay, 30% of the time, 20%, 10%, 40%, okay? This 5-degree rectangle shows this wind rose, and the length of the arrows indicates to you the distribution of wind from the different directions. The number of feathers indicate the Beaufort number. So right here you have 5 feathers, that means Beaufort 5. And the length, as I say, indicates the amount of time from each direction. So as you scan this chart, you can see the different wind roses. You can see here the wind is more balanced in direction than here. It's more predominant from the north and the west. Okay. Here's icebergs. Here's a triangle of an iceberg that was in a certain. These green arrows indicate currents of those ocean gyres that I showed you before. There are also lines on here. These black lines going in this direction are the magnetic variation, lines of magnetic variation. If you trace the lines down somewhere, you'll find a number on those lines that will tell you that it's 10 or 11 degrees east or west, whatever it is. Okay. Then, of course, there are cruising guides. There are the coast pilots. There's the sailing directions. The sailing directions en route to different locations. Local cruising guides. And these all give you strategies and weather expectations for this time of the year for this location. Radar, collision avoidance. You can use radar to identify and track other vessels, of course. You can also use it to identify land masses, ports, inlets, bridges, nav aids, and so forth. Raycons, which are the radar repeater nav aids that will show up on your radar. You can use it for measuring bearings and distances. You can also, in talking about weather, use it for tracking storm squalls. And you'll see a storm squall very clearly showing up on your radar screen, and you can use collision avoidance techniques to track those like this. So here is a plotting sheet called a maneuvering board. But basically, if I take my radar and I'm located at the center of this plot on my radar screen, if I plot the location of this storm squall here, and then let's say 6 minutes later I plot it here, I can then draw a line between those two positions. This is the relative position of the storm compared to me, and this is the relative motion of the storm compared to me, and therefore this is the closest point of approach of that storm. This is the exact same way that we use radar to plot collision avoidance tracking of other vessels. There's also internet weather data, and these websites I include for your use, and these are websites that I frequently use when I'm reviewing weather for boats at sea. And this we looked at before. This shows a surface level forecast, either a fax forecast that you can receive on your boat, but in black and white, or from the internet in color like this. But basically, this is the surface forecast for a particular date and time. And here are the weather systems, the low pressure systems. Here are the highs. Here are the isobars. This says developing storm here off the coast of Delaware. Here's a developing gale over here. Here's a cold front. Here's a warm front. Okay, so all the different attributes that we were talking about. These numbers in the black squares, the black and white, these are the barometric pressure. You see 90. It means 990 as a barometric pressure. This means 1,008 pressure. Okay, so the different pressures, 994, 980. And then this would be an example of a portion, small portion of a NOAA offshore text forecast that you can download off the internet. And at a certain date and time, it gives a synopsis. High pressure will build into the area, pass east of the waters. A warm front will occur, Baltimore Canyon to Hatteras Canyon out to certain location. Expect gale force winds tonight. Expect these wind strengths and directions. These seas, 6 to 12 feet, these are significant wave heights. So you have to use that Brett-Schneider distribution to estimate what you're going to see actually. Here's here's one page of a 7-day forecast. This shows the east coast of the U.S. Here's the west coast of the U.S. And it shows the lows, the highs, the cold fronts, the low fronts. This is day 3. It's a surface forecast for day 3 of the 7 days. And there's a series like this, so you can look at these and see what's going to happen out to 7 days. This, again, is internet download. Now, storm tracks, I'd like to just give an example of the east coast of the United States. This is an area where the prevalent tracks flow is shown by these red arrows. If I have a low coming out here off of Georgia, we'll have lows travel like this and usually turn northeast. They may go out to sea at this point, or they may continue up towards New England and off over to Britain. But this is a typical track. It follows in this area, pretty much follows the Gulf Stream in this area, and then departs from the Gulf Stream up here. And this follows pretty much the continental shelf right here. Here's 1,000 fathoms. Here's 39 fathoms. So the shelf drops off right here. And that's what the Gulf Stream does. Here is again the Gulf Stream flowing. And if I'm planning to sail from Norfolk to Bermuda, and the black line is my run line, this is my desired course, but I know I have the Gulf Stream flowing like this, the blue line, so I want to compensate for that. So before I get to the Gulf Stream, I'm going to head south of my run line, as shown by the green line. And I want to intersect the Gulf Stream maybe 30 miles southwest of my run line, okay? Because the stream as I enter it is going to push me roughly 30 miles to the northeast by the time I get across it. It's flowing at 2 knots or so. So I pick a point, aim towards it here. I know I'm going to be pushed up in that direction. My strategy is to use my my GPS and set a waypoint for my destination, say Bermuda, and use the VMG function of my GPS to advise me on how I should be steering and how I should be trimming sails. I find the best thing to do in crossing the Gulf Stream is to maximize your VMG to destination and not be as concerned with your track over ground. Now let's look at another issue, sailing in this area. If I'm doing exactly this, sailing in this direction, and I have a low develop at this point or proceed to this point, I'm going to be getting northeast winds from this low. I'm only showing the low here, but remember it's a big set of circles around here. I'm going to be getting northeast winds blowing right down the pipe in the Gulf Stream, and that's bad. I have wind against the tide, wind against the current, I mean, strong wind, strong current, big steep waves in the Gulf Stream, not a pretty sight. So I'd like to avoid this if at all possible. If, on the other hand, I'm crossing and I have a low passing north of my run line, now I'm going to be getting winds blowing from the northwest as the trailing cold front comes through. And that's beautiful. This is when you leave. You have a storm passing north of you, a low passing north of you. You want to be ready to leave on the tail of that storm just as it's beginning to clear and the wind pipes up to the northwest, because that gives you a tremendous driving force to get through this Gulf Stream very, very neatly. So this is the time to go on the heels of that storm. Here's a picture of the Gulf Stream offshore, and you see the wiggles in it, and you also see these eddies that are pictured here, these circles. And this is a warm eddy. Here's a warm eddy. Here's a cold eddy. Now the way an eddy forms is the Gulf Stream will get these meanders in it like shown here. And eventually this meander, remember it's flowing around this meander in this direction because the Gulf Stream is flowing from southwest to northeast. And it's flowing around this meander. Well, as this meander, if it deepens and gets longer, it will eventually teardrop and then break off as an eddy. And it's circulating this way, okay? And it traps cold water. Now, it doesn't show well on all of these, but you notice that this eddy, this darker green is colder water. The lighter colors are warmer water. You notice that this eddy is a warm eddy. It has trapped warm water in it. You notice this eddy is a cold eddy because it trapped northern water in it, so it's colder and it shows darker green, all right? Gulf Stream eddies look something like this. They usually circulate inward in the direction shown, and the way I'm showing the arrows. If you look at these, this is circulating counterclockwise, circulating clockwise. The warm eddy is clockwise, the cold eddy is counterclockwise. Now I'm going to say with all of this, I'm going to say usually, because there are exceptions to these. But the other thing is that the eddies themselves, I've been in eddies where I had currents of eddy current of 4.5 knots within the eddy. And if you have the electronics will measure that for you. But the eddy itself is traveling in the southwesterly direction. It's not traveling in the direction of the stream flow. Okay? So that concludes my presentation, and the important thing here is understand the dynamics of weather systems, mainly in order to minimize surprises. If I know what's coming, I can prepare for it, and I can be better prepared for it when it hits. For example, a storm squall, a lightning squall is going to hit you. Don't be complacent, prepare the boat and be ready for it when it hits. Wave action is the most destructive aspect of severe weather. The wind we can usually deal with by reducing sail, but the wave action is the real destructive force out there. Decide in advance what you will do in survival conditions. Will you heave to, or will you run off? Will you use a sea anchor? So decide in advance what your strategy will be. Have the equipment prepared, have the procedures prepared, instruct your crew, and practice.